In lesson 83, we're going to learn to integrate even powers of sine x and cosine x. A few lessons ago, we worked through integrating odd powers, and now we're going to be looking at even powers. To do this, we're going to use some new identities, which we are going to show why they're true using graphing. We could prove these identities also using the Pythagorean identities. We could prove them, but we're going to go ahead and show their graphs, and we'll see why they are true. So up here at the top, we have the function sine x squared, which is really sine squared x, which we use the form sine squared x. And we see this graph here, and it's still a sinusoid. So we can find the equation of this sine graph in a different form. So as we look at this, we see that we really have a cosine graph because it's got a midline here at half. So let's take a look at this. G of x we could also write as the midline's at 1/2, so we're going to put a plus 1/2 out here. We notice that this cosine graph, its amplitude, the distance from the midline to the highest point and lowest point of that graph is 1/2, so our amplitude is 1/2, and in fact it's -1/2 because it goes down first. So we got 1/2 cosine, and now we're going to look at the period. Well, the period here is not 2 pi, it's just pi. So we learned in the past that period for sine and cosine is going to equal 2 pi over k. Well, in this case, our period is pi, so pi equals 2 pi over k. And solving for k, well, in order for pi to equal this, k has to be 2. So k is equal to 2. And so we have 2x up here. We're going to go ahead and write it. G of x, we'll put the 1/2 minus 1/2 cosine of 2x. And these two things are the same. So sine squared is equal to this. Similarly, we can look at cosine squared. And writing the equation of cosine squared, here we see the graph of y, or g of x in this case, equals cosine squared. We still see that it's a cosine graph because it crosses the y-axis above the midline. So we could rewrite this g of x, it's up 1/2, so I'm going to make sure I add 1/2 to the end because it's moved up 1/2 because of this midline. Its amplitude is 1/2. In this case, we're going to put positive 1/2 because it's up first. And similarly, the period is pi. So if the period is pi, just from what we did up here, we see that k would equal 2. So this is going to be 1/2 cosine of 2x. And that is equal to cosine squared. So there we see those identities by looking at the graph and writing the equation in a different form. And so we can use those two identities to help us integrate even-powered trig functions. So here we want to integrate cosine squared x dx. So what we're going to do is we're going to make our substitution. Instead of putting cosine squared, we know that cosine squared is 1/2 plus 1/2 cosine of 2x. We see that there's a 1/2 in each term, so we can go ahead and factor out that 1/2. And now we can integrate that fairly easily. So the integral of 1 is just going to be x, and the integral of cosine 2x is going to be a positive 1/2 sine of 2x. We get the 1/2 because if we needed to check this, we would have to take the derivative of sine of 2x, which is cosine of 2x, but then we would also have to take the derivative of what's inside, which is 2x, which would give us an extra 2. And so we have to multiply this by 1/2. And so the integral of cosine squared x is 1/2 times x plus 1/2 sine of 2x. You could do a couple things there. You could distribute the 1/2 back in, or you could factor out another 1/2, but there's the answer. Coming to our next example, we have the integral of sine squared x times cosine squared x dx. And what we're going to do here is we're going to substitute for both of those. Then we won't have those squares there anymore. So we're going to substitute in. We notice actually that these are in the form a minus b times a plus b. And so when we multiply those, we'll get a difference of squares. So we get 1/4 minus 1/4 cosine squared of 2x. We notice we can factor out that 1/4, but at the same time we have this cosine squared of 2x. So what we're going to do again is substitute. We just have to be careful here because instead of having an x, we have a 2x. So this is going to be 4x when we substitute in. So we're going to factor out a 1/4, which that gives us the 1. From right here we have the 1. And this was our cosine squared of 2x, but plugging in to this equation we get 1/2 plus 1/2 cosine of 2 times 2x. So instead of having our 2x here, it's times a 2x. And so we see that we have this 4x right here. Simplifying from there, we can distribute the negative, and we get 1 minus 1/2 is 1/2, and then distributing the negative is a 1/2, negative 1/2 cosine of 4x. We can factor out a 1/2 from both of those, which gives us a 1/8 on the outside. And then integrating, we get x minus 1/4 cosine of 4x. And again, the 1/4 comes because of the chain rule. Here it's cut off a little bit, but we have the integral. We want to integrate sine to the 4th x dx. Well, this isn't sine squared, but it's close to it. We can actually rewrite this as sine squared squared. So this is really the same as integrating sine squared x squared. And so what we're going to do, we're just substituting in for this sine squared x, the identity here. We'll go ahead and multiply that out. So it's multiplying the squared out. We get 1/4 minus 1/2 cosine of 2x plus 1/4 cosine squared of 2x. We still have a squared term here. We have cosine squared of 2x, so we're going to substitute in for that squared using this identity here, which again gives us this with the 4x. Doing some distributing with the 1/4 gives us this. We have some like terms we can add together. We have a 1/4 and a 1/8 that can add together. That gives us 3/8. And then integrating that, we'll get the integral of 3/8 is 3/8 x minus 1/4 sine of 2x. Again, the 1/4 comes from, we already had the 1/2, but we need another 1/2 because of the 2x. And then plus 1/32 sine of 4x plus c. And so that's integrating even functions of sine and cosine. We're going to use these identities, so make sure you know these identities. Plug in so you can get to something where you don't have any more squared or anything to an even power. And from there you can integrate.